And also thanks to the conference organizers for giving me this opportunity to speak again at this conference. It's a privilege, and I enjoy coming here every year and talking about PostgreSQL, something new that is happening in the community, talk about it. So this year's topic is no different. I will be talking about something that is happening in the community and a feature that we are developing and we are looking forward to. So in fact, in this very room, the last presentation that happened was about GraphQL. And thanks to those presenters, they have set a good background and context for me to start with. However, this is slightly going to be different treatment of what graph databases are and how they are related to PostgreSQL. So we will talk about graph databases, of course, what they are. Then we'll talk about something called SQL PGQ, which is the SQL standard. And then we will talk about how we are bringing these two together and adding yet another feature in the battery of features of PostgreSQL to make it look less like a relational database and more like something else. So let's begin with introduction to graph databases. A graph database uses graph structures with nodes, edges, and properties to represent and store data. That's a simple definition of graph database. On the right-hand side, you will see what a graph looks like. There are two nodes there, rather three nodes, two of one kind, third of different kind, which are connected by edges. So the basis of any graph is the nodes, which represent entities. For example, here we see the famous Alice and Bob coming back. There are two nodes, one for Alice, one for Bob. And then there is a third node, which is for a group named Chase. So the entities usually represent people, product, locations, anything which can be called as entity. The edges represent relationship between the nodes, relationship between the entities that are being modeled. So in this case, you will see that there is an edge with label nose. Then there is an edge with label is member, label as members, and so on. So these three nodes, they are brought together by edges, and their relationships are depicted by edges. When we store the data in this form, that's what graph database is. And those who are familiar with the relational databases and have heard term entity relationship model, entity relationship data modeling, ERD, ERM, whatever you call, or ER diagrams, they would find it similar to see the link between the relational databases and graph databases. Ultimately, relational databases or their whole philosophy was built on something called relational algebra, which has its roots in the entity relationship diagram. So although people think that it's a very different paradigm, they are very close, and that closeness or that relationship goes back in history. In fact, graph databases, I would say, are precursor of relational database in that sense, although the paradigm as such is newer than that. Now, what makes it a database really, what makes this graph a database is the properties or attributes of node and the edges. For example, you will see that the node corresponding to Alice also has property age. It also has an ID, which is the ID of the node. Similarly, Bob has age. And then this group, which is of type Chase, again has a different property. Similarly, you will see some attributes there with the edges. For example, sins. There will be sins with the is member also, and then the corresponding IDs. And this together, because of these properties, usually these type of graphs are called property graphs. And this is one of the representation of graph databases called property graph databases. This is what we will talk about in the rest of the presentation. Just for the completeness, the other type of graph databases is RDF, Resource Description Framework, which is used for representing network and the resources and their relationship. But these two forms are interconvertible, but we will stick with property graphs for this presentation. So where do we see uses of graph database? They are almost everywhere these days. First and foremost, everybody is now exposed to social media, and the first and foremost use we find in social networks. In this case, the users, their content, the content that they create, the relationships between the users, their content. Content again can be multimedia. All of that is represented as a graph. And then that graph is exploited to find out, for example, who is influential user, or how the information is flowing through the society, through these users. Are there any rumors being spread in the society? That can be inferred from how the information is being spread. What are the current trends in fashion, in news, anywhere? That can be mined out. So these social networks, when they are represented in the as a graph, we are able to mine all that information easily. Well, a derived use case of that is recommendation systems, which again models users, but in this case, their likings, behavior, and then the relationship between them as graph to recommend products and services. For example, if there are two users with similar behavior pattern, similar social networks, and one of them likes a book, then there is a high chance that the other person will also like the same book, and you would recommend that book to the other user. The graph is used to exploit or mine this information about similarity in behavioral patterns. Fraud detection, will come to this in a minute. I will elaborate more on this. Again maps the financial transactions, financial instruments, users or entities, and their relationships into a graph and uses it for detecting frauds. Logistic supply chain management is another example, which models products instead of users as the nodes, and then the demand and supply chain channels are modeled as edges, again to find out how the demand is being supplied, what are the bottlenecks in this supply demand chain, and then optimize those things. So here is an example of one of the fraud detection techniques where the money gets transferred, or money or anything of value gets transferred from one entity, one person, to another person, in this case blue and orange, through many different financial instruments and many different unrelated users. Now imagine trying to find this pattern, find this graph, find this information in a relational database. This is all there in the relational database, right? If you look at the databases of banks, all information is there in those databases. But if we want to find such a pattern, it will be very, very difficult with just SQL. Whereas with graph databases, it's much easier to say that how is the money or the something of value flowing from account A to account B, or entity A to entity B, and which has in 3 to 6 steps, because that's usually how fast a fraud money would go. And it's much easier to specify and, of course, then match that pattern to the underlying database to find all such patterns and all such accounts where the money has transitioned from. If we model this as a graph, or model this as a graph database. Any questions on the concept of graph databases, the theory behind it? Okay, so what I'm going to do next is I'm going to now come back from the graph databases to the SQL world and show how these two can be linked through something called SQL PGQ. So what is PGQ? Property graph queries. In fact, SQL PGQ is now a SQL standard, 16th part of SQL standard. It's an extension to SQL, which means it is part of the SQL. It's just an additional thing to SQL. You can use it as part of your normal SQL. And what it does, maps a SQL or a relational database to a graph database. It can be used to view the relational database as a graph database and then query it. It's mainly for query, not so much as for the manipulation. Manipulation still happens through the regular SQL. So what it does, it maps relational tables to set of nodes and edges in the graph. Then it classifies these tables by labels and then exposes columns of the underlying relational tables as properties of nodes and edges. These are the constructs that are used to do this mapping, where the top level object is property graph. Property graph has one or more of vertex tables, which are the relational tables which get mapped to nodes in the graph. Each of these tables, usually their primary key becomes also the key for the nodes that it exposes, identifying each of the nodes. Each of these tables can have multiple labels, classifying, allowing it to be part of one of the classes in the graph, or classes of nodes. And each of these labels can expose the underlying columns as properties. So through this, we have a completely different view of the underlying relational data, and we'll see it as a picture. The second part is edge tables, which is basically the underlying relational tables that will be mapped to the edges in the graph. Each of these has a source key, which points to the source of that edge, and the destination key, which points to the destination node of the edge. So together, source and destination identify the two nodes which the edge connects. And again, just like vertices, edges can have their own labels, and each of these labels again can have properties which are basically exposing the underlying columns. And that's so that once you create this mapping, your graph is ready. You don't have to do anything. You are ready to query the underlying database, which is a relational database, as a graph. So all you have to do is just create this property graph. In a way, it's very similar to how we create views, but it's much more dynamic than what create view can create. The second part of the standard is query constructs. And there are 4 constructs here, all which become part of your regular SQL query. So you can say select star from table 1, comma, graph table. Inside graph table, you can put whatever you want to get from the graph, underlying graph. Another comma, another table. So you can mix the graph query along with the rest of the SQL. It just gels very smoothly, and you can run SQL query. So the first construct is graph table, which specifies what property graph to use, which of the mappings is to be used for this particular graph query. The second is match, which defines the pattern of paths being that need to be queried. So the first construct there shows the vertices. The second construct shows labels, and the arrows usually connect vertex to edge or vertex to vertex, and it gives a pattern, something very similar to what we saw here. You know, this is a pattern. Like we already see match. This is the pattern that will be part of the match. And but before match, what we add there is the underlying, the mapping that is to be used for this pattern. Where clause we are all familiar with, which is a clause to filter the data. In this case, the where clause can be placed at 2 places, one with each of the vertex and edge to filter the, within each vertex and edge pattern, like this. This is vertex pattern, this is edge pattern. Inside that you can put a where clause which will filter the edges or nodes of that particular type. And then you can append where clause at the end of the pattern to filter the paths that satisfy that particular given pattern. And at the end, just like select clause, we have columns clause here, which projects the properties of the nodes and edges in a given path. Okay, I think this will bring all of what we just discussed together. On the left, it's the graph that we are familiar with. And on the right is how it looks in the relational database. So there is a person table, there is a group table. These will get mapped to the vertex tables. And then there is nose table and member of table, which will map to the edge tables. What you will see here is that every node in this graph, for example, Bob has become a row in person's table. Alice has become a row in the person table. Similarly, Chase has become a row in group table. So what used to be rows in the relational data or relational table now becomes a node. Every row of the vertex table becomes a node in the graph. Similarly, you will see these edges here are the rows from the edge table. So every row in the edge table becomes an edge in the graph. And the way these are linked through the keys. Usually the foreign key and primary key on the relational tables become the keys for the nodes as well as the edges, which link the nodes and edges in the graph. And so let's see how it looks like in SQL when we create a property graph, or how the property graph in SQL looks like for this. So let's call this property graph Gymkhana, which is usually a term for club, at least where I live. It has two vertex tables, person and group that we saw. And the table person is also labeled, has the same label, person. And this label is exposing the properties ID, name, age, which are the columns in the person table. But let's say group has a label sports group. So we don't need to have the same name, same labels, or labels have the same name as the corresponding relational table. They can have different names. And also, the properties don't need to have the same names as column. You can use as clause to project a column of a different name to a property of a different name. But in this case, let's keep it simple, and it exposes the column group ID and name onto basically the same columns as properties of label sports group. Coming to ages, well, I have added some fun here. So we have age tables, which is knows and member of, that we have seen, for which we give the source and destination keys. Both is person ID, because knows is a relation from a person to another person. So it gets, the source and destination all look same, but these IDs will be different. It will be the IDs of two different persons connected by relation knows. And this age has two labels. One is its relations, because it's a general type of relation. But it also has another label, knows, which is a specific type of relation. And you will see these two labels expose different properties. So the first label, the relation, exposes ID for that relation, and then the since, which is actually the attribute. And then knows exposes ID, since, and how. I mean, how these two people came to know each other, that information. So even if, although I have shown this just for ages, it's also true for vertices that they can have multiple labels, each projecting different properties. And not only that, we can see when we come to members that member of also has labeled relations, and knows also has a labeled relations. So let's come to member of. Again, the source is person, but the destination has changed. It's group ID, because member of is a relation between a person and the group of which it is member. It falls generally under the category of relations, so it has a labeled relation. And all the labels of the same type or with the same name need to project the same properties, so it's exposing properties ID and since. But the member of age table also has another label, member of, which has an extra property called type, which is the type of membership to that group. Now, once we have established this mapping of how the four tables that we saw in the first figure, person, group, knows, and member of, once we map them to the graph, it becomes easy to query them. And the beauty of this is the graph query is also imperative, just like SQL is. It tells what we are looking for rather than how to look for it. So in a sense, these two gel together. And in this case, the first query is people who don't know each other but are members of the same group. So you say that I want a person B, which is connected to group C, and another person A, which is also connected to group C, the same group. but who do not have any connection between them. Now this, I have simplified a bit. This last thing, those do not have connection between them, has slightly complex structure here, but let's simplify it for this presentation's sake. And you will see that it's very expressive itself, that you want two people who are connected with the same group. And A and B indicate that we want two different people, not the same person again. Well, what you will do with it, you will introduce those two people and, create a, let them become acquainted with it, and that's how the social network in the Gymkhana increases. Let's look at slightly complex query in this thing, where we want to find all the acquaintances which were made in this club, in this Gymkhana, so that they can advertise it as, socialization platform. Now you will see what we want to find out is, again, person A and person B who know each other. So there is this K knows in between. And then we want these A and B to be member of the same group by two different ages. That's why we have MA and MB, even though both of these point to the same age table. But the fun is here, we are saying that this vertex is of type group. So A should be connected to C, which is of type group, and B also should be connected to C, and we have already declared that it has to be of type group. And that's how we complete this query, which will link all the A and B, which know each other and are also member of the same group. Additionally, we add a where clause here, which says that they should know each other only after they have joined group, which is indicated by C. So now imagine this is 1, 2, 3, 4, 5, 6, 7, 8. 8-way join, trying to write an 8-way join and a couple of unions below that, and trying to put a where clause just using SQL. It soon gets complex. We'll see more complex queries of this type. And in PGQ, it just becomes very simple to, this is still simpler than writing SQL to do these kind of queries. Okay, before we jump to more complex things, any question till now?
So graph is a complex form of data, right, among all the other formats. So why do we put them in a relational database which has a lot of joins in the background? End of the day, gives a lot of performance bottlenecks.
Okay, I'll touch upon this point. You don't, well, if SQL PGQ in PostgreSQL gets to a level where graph database users are fascinated by it, I will be glad, but it's the other way around. You have the data in relational databases, which you want to query like a graph. You have already a graph. Ultimately what we saw first, right? A relational database is first and foremost a graph. It's an entity relationship model. It's a graph. So the relational data is already in a form of graph. What we are doing is we are adding constructs to SQL to expose it and query it as graph. So it's the other way around. You have data in the relational database. You want to treat that data as a graph.
So the underlying tables you mentioned, they have references to the other tables. In one of the examples, the relation was being reused on both sides. So how does the references, how do the type resolve there?
Okay, that's a very good question. In fact, I should have. So that's the member of thing, right?
Yeah.
Now, so in graphs, what you will have to do is you will have to store the age bidirectional. You know, even though it's the same age, you will have to store it in both directions. In SQL, you can just flip the definition of member of, make it is member, and have the destination and source flipped. Label relation remains like that, and instead of member of label, you will have is member. And the same relational table will act as the age in opposite direction.
Okay, so all that is being done behind the scenes.
No, in this case, you will have to add it. I mean, if you
okay.
want the reference to go in the other way direction, then you will have to add another entry in age tables.
Okay, okay. Thank you.
So last year we got a graph query language standard, right? So how is this compliant with that?
I'll come to that. I'll reserve that question for the end.
Yeah, okay.
Okay, for the sake of time, let's proceed, and we'll try to take as many questions at the end. Otherwise, we'll take those out of. Okay, so far so good. Just 4 tables, but imagine this, and this is by no means how a relational. An actual database being used looks like. It's much more complex. But so this is kind of graph of an online shop or online business where there are customers in pink, the tables related to customers in pink, their lists of orders or wish list in green, their payment instruments in yellow, and the products that are being sold here in another kind of red or pink. So there are 1, 2, 3, 4, 5, 6, 7, 8 tables which represent node or entities, and then 16 tables which represent ages. So there are 24 tables in the underlying database, and this is the ER diagram for it. What we have to do is just map this ER diagram to the property graph, and then your database is ready to look like a graph database. The fascinating, at least to me, feature of SQL PGQ is that each of these tables can have millions of rows, or even billions, trillions, whatever scale you want. All of that data, imagine visualizing a graph which has billions and trillions of nodes and ages in it. But, I'm sure we can't imagine. But instead, SQL PGQ or ER diagrams allow us to represent that whole graph in a very compressed manner, maybe on a sheet like this large. We are able to visualize that. Furthermore, SQL PGQ allows them to be labeled and classified. So this graph actually can be further compressed into just 4 types of nodes and 3 types of edges. And then it can be queried. Again, imagine, we'll in fact see an example soon. So this is how you will map that entity relationship model into a property graph. It still fits in one slide, by the way. And then let's see how we will write a query to find all products which are paid by a credit card. So that, you can, let's say, give more promotions on credit card or offer EMIs, anything you want to do with that thing. Imagine writing a SQL query now with those 24 tables involved and so many unions. I think there will be at least 9 unions there. Instead, I mean, that query would just flow pages and pages. Instead, all you have to do is write this single line where you say that we start from this part where we connect orders with the product. We find all the products in all the orders. Then connect it to the payments here. And again, you will see the familiar construct where the same variable is bound to two nodes, two vertices, which says that it's the same order here and here, and then connect it with the payment method so that now we know that all the products which are paid by the credit card, and just project the name out of that. So this is how we bring, this is the match clause, this is the columns clause, where the only thing that is missing here is a graph table clause, but I think I'll leave it outside. It just comes here, graph table, what are shop, comma, match, then this rest of the thing. And then you can get all the products which are paid by credit card. So what are the advantages? I think they are apparent by now of SQL PGQ. It's well integrated and leverages existing SQL infrastructure and expertise. We don't have to go find another set of DBAs, programmers, application developers to use it. It very well gels with the rest of the SQL relational infrastructure. It's standardized. It's ISO standard, so it is easy to port your applications. They will interoperate easily. Most important, you can query the database just like it is relational, or you can view it as graph, and all of this happens in single system. You don't have to take your relational data, move it to graph database, query there, and then maintain that link between the relational database and the graph database and keep on updating it and take all the burden of that maintenance. Just flip the coin. On one side it's relational, on the other side it's graph. Now as PGQ becomes more and more used, the query patterns that emerge from PGQ, like unions and joins, of course, we'll find ways to optimize those queries. And then the rest of the SQL optimizer will continue to work and operate for the graph databases. We don't have to invent another query optimizer for the graph databases. And all of this comes with all the good things about relational databases, SQL databases, asset guarantees, tools, and whatnot. Transactions. And for now, at least, we treat it as something that will let relational data to be used as graph. I don't think people who are looking for graph databases exclusively will yet come to relational database. But yeah, that could happen also. And that's what the next slide is about. The graph databases will continue to exist. They will provide flexibility, storage, and performance, which are their forte. And they will continue to be flexible. You will be able to add nodes, properties, labels on the fly, which SQL PGQ doesn't. SQL PGQ requires a predefined schema. Well, there is a way to make it flexible, but it's a bit complex. They will continue to have optimized storage for storing graphs. And of course, they will continue to give better performance and optimize for it. Well, that's been what SQL PGQ about. We haven't, this is PostgreSQL conference. So in PostgreSQL, there have been attempts to bring graph databases to PostgreSQL. And one of the famous extensions is Apache Age, which is the successor of Agents, which was a fork of PostgreSQL. It provides Cypher-like graph query language, which needs to be wrapped in a function call. So the interface is not natural. It's not that intuitive. But it still jails well. And then PostgreSQL is used as a storage. The other thing is PG routing, which is lesser known, but it is used along with PostGIS for geospatial routing facility. And it cannot be used for general graphs. What we are doing is we already have a patch on Hackers, which implements most of the DDL, create, alter, drop. It has extended supports to all the tools, dump, restore, upgrade, all the tools that you love about with PostgreSQL. And in the queries, we have basic path pattern specifications supported. Some complex things like quantifiers, embedded patterns are still not implemented. But as happens with any PostgreSQL feature, once the first drop lands, the next enhancements will follow. It supports a label disjunction, and most important, it is well integrated with the rest of the SQL. You can just drop your graph pattern in the SQL query that you are writing. So it's a patch authored by Peter Eisentraut, who is member of SQL Standards Committee, also core member in PostgreSQL, and myself. It is proposed on Hackers. It's feature complete as of what I described in previous slide. But it's unfortunate we won't be able to get it in PG18, which is the release happening at the end of, which will code freeze at the end of this month. But hopefully we'll have it in next release next year in PG19. The request for the community here is we require people who can review and test these patches. You can be reviewing anything, functionality, documentation, code, as per your liking and your expertise. There are very few people who have both expertise, graph database as well as SQL. So those who have, please, this is a request and call for volunteers to review these patches. And also testing. It's very much welcome. We really appreciate those efforts. Last but not the least, well, PostgreSQL will never become a graph database. Take my word for it. But it does not stop from users taking it to the level of graph database. It already has the extensibility that can be exploited to make it a graph database. We have pluggable storage method where we can optimize storage for graphs. And then the query rewrite rules, custom plan nodes, planner hooks, all to optimize those queries that will get generated, that are the graph queries. Well, this is slightly dubious, especially whether it will get GQL support. I think it should be possible if we see pluggable parser being a reality with PostgreSQL. Babelfish, those who remember, is a plug. It's a step towards that. But if we get the pluggable parser, I think GQL also can become a reality in PostgreSQL. Otherwise, we have Apache Age, which supports Cypher and GQL. And yes, Microsoft has a bunch of talks. Please attend those, visit our booth. And thank you.